So, as I mentioned earlier, this is going to be using the recurrent neural network for this. We know that the input is going to be a sequence, output is going to be a sequence, and HT is computed in this fashion, okay, using the previous memory and the new input. So, as I mentioned, this hidden unit could be an LSTM or GRU cell. So, every box is trained to predict the next word in the sequence, and then it learns the probability distribution. For example, given a single layered one, right, and let me use this as y hat. This is our Rn. So, if I input, let us say the here we expect the output as book, right. So, every time we are learning the next word in that sequence, and it remembers the previous hidden value using this matrix. And then output at each time is again a probability. It is, I am bringing in what we had done in the language model, the probability based language models. So, it depends on the previous words, right. So, the word at time t depends on the words it had seen earlier, right. It is conditioned on these words that it had seen in the earlier time space. So, output is a softmax layer. So, if you have 40,000 as your vocabulary, the distribution is going to have 40,000 values. This also we understand well, I guess, right. And then the probability of the sentence is the computation of the probability of each of the word that we have identified. Okay, so, this is what exactly we are computing in each box. Okay. So, little more into the diagram side rather than looking at the sentences. So, we have an encoder, we have a decoder. So, we are going to be inputting x1, x2, xt, and we are going to be outputting y1, y2 and yt, and this time slice is different, this time slice is different. Okay. So, in this case what we do is we compute the context vector at the end of the encoder computations, right. Yeah. So, we are going to be feeding that. So, this is nothing but the encoded message, like we can call it. This is the encoded message of the input sentence. It contains some numbers. We are going to be using that as an input as well. So, in this case again there is a HT minus 1 that comes in, right, and then there is a context vector that is coming in, and then there is an input that is coming in into the decoder, right. So, we know that these two phrases well beforehand, right, that is a parallel corpora that we have. So, when we input the context into this and then the input word of this, and we are going to be getting an y1. So, we know that we have to expect y1 at this and so on and so forth. So, it goes on until yt. So, this is a very simple model. So, once the end of sentence is detected, so there will be a separate end of sentence and a start of sentence, which I am not showing here. When that is detected, we know that okay, it is time for the back propagation. So, then it comes back and then trains all the weight vectors along the path it passes through. Okay, so, this is a very simple model for the translation, because this is the first one that came into the world in 2007. 14. So, the only interesting aspect that we have is the context vector that we have created. So, encoder creates the context vector which has encoded all the important things or the all the words in it as a vector, and it is fed as an input to this. Okay. So, it learns to map the input sentence of variable length into the fixed dimensional vector. We have we've seen that. It learns to decode a fixed length representation back into the variable sequence. Then the model learns to predict the sequence given the sequence. Given the entire sequence, it learns to predict the entire sequence. Okay. And then the time space, as I mentioned, would be different. As I mentioned, as part of the RNN model, every symbol is read sequentially. So, X is a sequence containing x1, x2 to x3, and Y in bold represent this, and every time one word is read at a time. Hidden state changes according to this equation. Okay, we know this as well, right. Based on our experience in the RNN, we know that the hidden values at time t depends on the previous memory state as well as the new input that is coming in. Okay. So, we change the hidden state according to equation 3, and then C is the summary of the hidden state at time t. At the end of the first encoding session, we have the summary available as C. Okay. So, that encoded all the symbols in the sequence. All right. So, when going to the decoder part, we saw in that box, right. This is another RNN. This is trying to predict the next symbol as in the encoder as well, and it generates an output sequence. So, in the decoder part, in the encoder part, we generate a context vector or a summary vector, whereas in this case we are generating an output sequence. Okay. And it depends on the previous state that we had seen earlier. And the output is conditioned, as I mentioned earlier, the output and the hidden state or the memory is conditioned on the summary from the encoder. That is what we have used as C as our symbol, and the previous hidden state. So, this is, let us assume that this is our decoder, and then we have the context vector that is coming in, right. So, here is our y1, and this is what we have to predict. This C comes in from the encoder part. Okay. So, this y2 depends on the context and then the previous hidden state of the decoder and the new input that we provide, correct. So, this now has the information about the entire sentence that we had used in the encoder, and that is what is passed along here. Okay. So, what we get again is a conditional distribution. Again, if you use softmax, depending on the vocabulary, you have that many values found in that. Okay. What at the end of it, what we are estimating is in the decoder part, at the time slice t, the value of this is estimated by using the previous sentences and the summary that we have received. Okay. So, this value is conditioned on the previous inputs as well as the context that we have gotten from the encoder statement. Okay. So, next is how do we estimate the model parameters, right. So, every time when we do the training part, there is an error that happens. So, we are estimating J1, J2, Jt. So, theta is our model parameters that we are going to be estimating. Theta is nothing but the weights that is connecting the output to the hidden layer, and then the weights that is connecting the hidden to the hidden, weights that are connecting to the input to the hidden layers, and so on. Supposing if we have a more complex network, there will be more parameter that we need to estimate. So, this Jt is something that we want to estimate, right. We want to maximize that. So, let us use the log likelihood, okay, and theta is this set of model parameter that will be learned during the back propagation through time, right. And xn and yn are the sequences that we are providing as input and output. This is coming from the encoder, and this is what we are going to be expecting as this, and then compute error at every stage, and then back propagate, and then make the system learn the weights every time until it is minimized. Okay. So, this I think again is very familiar to you. So, what I have given here is for your understanding. I have brought some of the back propagation through time slides into this. So, as I mentioned, what are the parameters that we have to learn? We have to learn V, W, and U here. So, V is the one which is connecting the hidden state to the output unit, and then we have the input coming in from the sequence, which is connecting the hidden state with the matrix W, and then the previous state is connected using U, and then we minimize this and using the partial derivatives, and finally obtain a J value, right, a collective value for J. Okay, for every output value in the decoder, there will be one J which is summed, and finally a score is obtained. We want to use a gradient descent algorithm to find out whether the error is really coming down or not, or adjust the input parameters and then initial weight condition and so on to make sure that we follow this path. Okay. So, once it is minimized, we can stop at certain point and then finally say that the system has learned. So, in this way we learn V, W, and U, and then when we do that, we know very well in this normal RNN we have two problems. One is the vanishing gradient, the second one is exploding gradient. Right. So, we want to really avoid this, which is very crucial. We can clip the gradients to very quickly solve this exploding gradient problem. We had seen all of this earlier. So, what the people who have developed this system had done is created a small cell very similar to GRU, where you have an reset and a forget gate. Okay, so, you can call this as an update gate. So, in this case you want to maintain that there is a gradient available for you to differentiate when you do the back propagation through time. Okay, so, these gates really condition the value in such a way that there is always gradient available for you, they do not really vanish. One more advantage, if you say it from the mathematical front, that is what you can say, but if you want to do it from the natural language perspective, we want to retain certain important words even though we have progressed in time, we do not want the system to forget it. So, we retain some of the important elements using this particular combination of cells that we create as part of the RNN. So, you can just throw that small h out there and then input this unit, and every hidden unit will contain this particular cell. So, only problem is we add more equations to the system. All right. So, we have a new hidden activation cell which helps us in terms of solving the vanishing gradient problem by making the values continuously differentiable. So, we have a reset gate. You may want to look at the diagram earlier and then see how the reset gate is obtained. So, using the weights connecting the reset gate and the input for the jth element vector, and then this is the previous memory connecting the hidden units, right. So, this is the weights connecting the hidden units, this is the previous state, okay, and then you have a sigmoidal function, you get it, okay, and then you have a value, and this is your jth element vector. In the same way, we can get the update get value as this. Okay, again there is a sigmoidal. There is a weight connecting the input and the update gate, and then again this is the same that we had seen here, okay. And a new state is obtained and a new memory is obtained by using this update gate, okay. And finally, the output hidden states are combined using the reset gate and the update gate, okay. In this particular presentation, I am using this paper, okay, for the presentation. So, you may want to go and then look at this paper, and this is the title on the properties of the neural machine translation encoder decoder approaches 2004. There is also one more paper earlier to this written by the same author that talks about the standard model. I think some of the gate that I mentioned is found as part of the paper written by Cho. That is the first paper that came out in the translation using the neural net model. All right. Okay. So, if the reset value is equal to 0, the hidden state value is reset with the current input states. I think we know about this. We studied in detail in the LSTM as well as in the GRU. The update gate controls how much information from the previous hidden state should flow or carry over to the current state. Okay. Units, they during the training they automatically learn to capture short term dependencies, okay, and then they also capture the long term dependencies on its own during the training process. Okay. So, this is one expanded version of the sequence translator. So, here the English is the input sentence, and then the output is the French sentence. Okay, so, you can have multiple hidden units as mentioned here. You can also have the hidden units traversing back in this fashion. If you want to make it more complex, so that all the hidden states contain some information about all the states. Okay. So, when we do this, usually the data related to this is found here. So, when we do the backward part, the reverse one, again the whole thing is translated back into this, right. So, this is one way of training the network as well. So, again you can use the same model. I am not going to be drawing all of that. So, there are various variations that you can bring in into this. Okay. One using the unidirectional or bidirectional, as I mentioned earlier. You can bring in more number of hidden layers and units, We can use a very plain vanilla to do this. We can bring in LSTM as part of the hidden units. We can bring in GRU, and you can also have the choice of learning algorithms, and you can bring in choice of error mechanisms as well as part of that, right. So, the permutation and combinations are huge in this case. So, you can have various different combinations of models available for the translations. Okay. So, it can also be represented in one simple way in the rolled fashion, or you can just have values going in this fashion also. You can have multiple of this and pass the input directly into each of those and pass the output of that into various stages rather than sequentially doing it. Okay, the application that we have for this is, as I mentioned, you can use this not just for translation, we can use for summarization, dialogue understanding, and then code generation. You can generate C code, you can generate Python code, or you can also generate some technical papers using this. Okay, so there are a lot of application people have tried. You may find more than what I have listed here. Okay, so we have described a model where there are two RNNs. One is used for encoding, another one is for decoding. The encoder encodes the sentence into a context vector, and then the context vector is fed in as input to the decoder, and then the decoder starts using the values that are coming in from the encoder and from the previous hidden state of the decoder and the input values, and start creating values for the parameters which we just use as theta. So, they are u, w and v. Okay. And we use an error mechanism and find out how different y1 is from the actual expected output, pass the error back using the BPTT, and train these models okay, for so many number of hours to finally have a translation model, which when provided this sequence will give you the output sequence. So, people have used a huge corpus or rather parallel corpora to do the training. I think in one case they have tried it for 5 days. They trained the system for 5 continuous days. Okay. For large corpus, I think you can't avoid this. For about 3,000 sentences in English and French, okay, it took close to about 4 hours in my small computer. So, thinking of a few 100,000 or a million pairs of sentences, 5 days is nothing. Okay, so, in the space where we have lots of computing power, neural net really provides the capability in terms of doing a good job in the translation, but you have to be patient with respect to the training. You should be very good in terms of choosing the right input parameters for the initial states. Okay. That itself is a good research topic, and you might find them in various other papers of machine translation. In this case, we have just used the entire sentence as a context for translation. So, later we will also use another model where the context is broken down into smaller pieces, and then how those smaller pieces can really help in terms of doing a better job. Okay. All right. So, for this session, I have used 2 papers. So, one is this, and I am not finding the other one. Maybe you want to search for the author Cho and others, and that paper gives you the model that we have just described.